If you think about a regular computer, it's all about light switches, right? On or off, 0 or 1. But quantum computers, they're more like a dimmer switch, but a dimmer switch that lives on the surface of a sphere. Today we're going to get hands-on with the dials that control that switch, the quantum gates. We're going to see how these gates don't just flip bits from 0 to 1, but actually perform these beautiful, elegant rotations in space.
So here's the plan. First, we'll get a feel for the qubit by visualizing it on something called the Bloch sphere. Then we'll dive into the basic single-qubit gates and see them for what they really are, geometric rotations. After that, we'll see how the CNOT gate lets us connect multiple qubits and create that wild thing called entanglement. And finally, we'll bring it all home and wrap up with the key takeaways. Sound good? Let's get started. All right, first things first, let's build our foundation. To really get what quantum gates are doing, we have to understand what they're acting on, and that's the qubit. We're going to take its algebraic definition and turn it into a really nice, intuitive geometric picture. Okay, this equation right here, this is the heart and soul of a qubit. See, it's not just a 0 or just a 1. It's some blend of both, this superposition of the 0 and 1 states. And those Greek letters, alpha and beta, they just tell you how much of each state is in the mix. But here's the key rule, the only rule you really have to remember. When you square the magnitudes of alpha and beta, they have to add up to exactly 1. It's kind of like a probability budget. You have a 100% chance of being somewhere, and you have to spend that budget between the 0 and 1 states. This simple little rule is exactly what forces the qubit state to live on the surface of a 3D sphere. So, the big question is, how do we actually move a qubit state from one point on that sphere to another? Well, we use a special kind of mathematical operation called a unitary matrix. Now, that sounds fancy, but in the world of quantum computing, we just call them gates. That's it. They're the basic instructions that tell a qubit how to change its state. And under the hood, it's all just matrix multiplication doing the work.
And this is where it all clicks into place visually. The Bloch sphere is our map. It gives us a perfect one-to-one picture of every single possible state for a single qubit. Think of the North Pole as being our pure +0 state, and the South Pole as our pure +1 state. And every other point on the surface, that's a unique superposition. So applying a quantum gate is really just rotating the state vector from one point on this sphere to another. Simple as that.
Okay, time for the main event. Let's see how this all works in practice. We're going to look at the most fundamental single-qubit gates, and for each one, we'll understand it not just as some abstract matrix, but as a very specific, very intuitive rotation on our Bloch sphere.
First up, the Poly-X gate. This is basically the quantum version of a classical NOT gate. It's a bit flip. So if you're starting at the North Pole in the 0 state and you apply the X gate, it literally rotates your state vector 180 degrees all the way around the X-axis, landing you perfectly at the South Pole, the 1 state. It's a clean, perfect flip.
Now the Poly-Y gate is similar. It also does a 180-degree flip, but this time it's a rotation around the Y-axis. And you'll notice in its matrix, we've got those imaginary numbers, I. This gives the rotation a totally different character than the X gate. You can think of it as not just flipping the bit from 0 to 1, but also tweaking its phase, which is a really important quantum property we're about to see more of.
And that brings us to the Poly-Z gate. This one's a bit different. It performs a 180-degree rotation around the Z-axis, the vertical axis of our sphere. Now what's interesting is, if you're in the 0 state at the North Pole, it does nothing. You just spin in place. But if you're in the 1 state at the South Pole, it introduces a negative sign. This is what we call a phase flip. It doesn't change the probability of measuring a 1, but it changes the quantum state in a really subtle way that becomes absolutely crucial when qubits start to interact with each other.
Okay, get ready for the rock star of quantum gates, the Hadamard, or H-gate. I'm not kidding, this is one of the most important gates in all of quantum computing. You could say it's the engine of superposition. Without this gate, creating that 50-50 blend of 0 and 1 would be way, way harder. This is really the key that unlocks so much of quantum's power. You can think of the Hadamard gate as the great equalizer. It takes the pure, certain states of 0 and 1 at the poles and performs this 180-degree rotation around a weird diagonal axis, halfway between X and Z. And where do they land? Perfectly on the equator of the sphere. Any point on the equator represents a perfect 50-50 mix of 0 and 1. This is the ultimate state of superposition.
The phase gate, or S gate, is a much more delicate tool. Like the Z gate, it leaves the 0 state alone, but for the 1 state, it multiplies it by I. On our Bloch sphere, what does this look like? It's a 90-degree, or pi/2, counterclockwise rotation around that z-axis. It gives us much finer control over the qubit's phase than the big 180-degree flip of the z-gate.
And check this out. This is so cool. It shows you how these gates compose. If you apply the S gate once, you get a 90-degree rotation. If you do it again, you've just done another 90-degree rotation. That's 180 degrees total, which is exactly what the Z gate does. So mathematically, applying the S gate twice, S squared, is literally the same thing as applying one Z gate.
So far, everything we've done has been on single qubits, each one living in its own little world on its own Bloch sphere. But the real magic, the true power of quantum computing, happens when we make these qubits talk to each other. And that brings us to our very first 2-qubit gate, the controlled NOT, or CNOT. This is how we start to build connections.
The CNOT gate is our first look at a 2-qubit operation. And honestly, the logic is super simple. It has a control qubit and a target qubit. It just looks at the control qubit. If that control qubit is a 0, it does absolutely nothing to the target. It just leaves it alone. But if the control qubit is a 1, then it performs an X gate, a bit flip on the target. That's the whole rule.
So let's just trace this out. If the input is 0, 0, the control is 0, so nothing happens. Output is 0, 0. Same for 0, 1. But now look at 0, 1. The control bit is 1, so boom, we flip the target bit. We get 1, 1. And for 1, 1, the control is 1, so the target flips from 1 back to 0, and we get 1, 0. By itself, it just seems like a simple, conditional if-then operation.
But what happens if the control qubit isn't just a 0 or a 1? What happens if we put it in a superposition, where it's both at the same time? Well, this is where things get really, really interesting. This is the classic textbook recipe for creating entanglement. Here we go. Step 1, we start simple, with 2 qubits both in the 0, 0 state. Step 2, we hit that first qubit, the control, with the Hadamard gate. That puts it into a perfect superposition of 0 and 1. Now for the magic. Step 3, we apply the CNOT gate. Since the control is now both 0 and 1, the gate's logic sort of happens to both possibilities at once. The part of the state where the control is 0 does nothing, but the part where the control is 1 flips the target. The result is this incredible state, a Bell state, where the 2 qubits are now locked together. They will either both be 0 or they will both be 1. And that spooky connection is what we call entanglement. It means the fates of these 2 qubits are now fundamentally linked. If you measure one and find out it's a 0, you know with 100% certainty that the other one is also a 0, even if your friend took it to the other side of the galaxy. This non-local correlation is a massive resource that powers quantum algorithms.
Phew. Okay, we have covered a ton of ground, from single qubit rotations all the way to generating entanglement. So let's just take a breath, step back, and really summarize the big picture here.
Here's your cheat sheet. The main takeaway is that each of these core single-qubit gates we talked about corresponds directly, 1-to-1, with a specific rotation on the Bloch sphere. The moment you start visualizing these operations as geometry instead of just abstract matrix math, it all becomes so much more intuitive.
So, if you're going to remember 3 things from all this, let it be these. 1. Quantum gates are just rotations. They are geometric turns. 2. Because of that, these operations are unitary, which is a fancy way of saying they are always reversible. You can always rotate back. No information is ever lost. And 3. 2-qubit gates like the CNOT are our primary tool for creating entanglement, for weaving the fates of individual qubits together into a powerful correlated whole.
And that's really what it comes down to. These simple gates, these fundamental rotations, they're like the letters of an alphabet. By stringing them together in really clever ways, we can write the words and sentences that become these incredibly powerful quantum algorithms.
And that leaves us with a pretty amazing thought to end on. Every quantum algorithm, no matter how complex, is really just a carefully choreographed dance of these simple rotations. So the real question for all of us is, what currently impossible problems can we choreograph a solution for, now that we know the steps to the dance?